Alright, example 2. Like I said, I'm going to show you one of each. Okay, example 2 is actually going to be a right tail test, and you'll see that when we start working this problem. Okay, so here's example 2. Is the diet practical? Alright, when 40 people use the Weight Watchers diet for 1 year, so sample size is 40, their mean weight loss was 3.0 pounds. Assume that the standard deviation of all such weight changes is 4.9 pounds, and use a 0.01 significance level to test the claim, here comes our claim again, that the mean weight loss is greater than 0. Okay, greater than tells you it's going to be a right tail test. So the only difference is how we're going to set this up. Alright, here we go. Step 1, I'm going to list out all my information. N is 40, X bar is 3.0, standard deviation is 4.9, mean of the population is 0, alpha 0.01, okay, number 1, stay HO and H1. Okay, remember HO is always that the mean is whatever it is in your claim. H1 comes from the sentence that's talking about your claim. It says test the claim that the mean weight loss is greater than 0. Alright, this means I'm doing a right tail test. Okay? Step 2, calculate your test statistic. Same thing as we did before. It's the sample mean minus the population mean over the standard deviation over the square of the sample. Alright, so I'm going to get 3.87. Notice that this time it's a positive number because I'm doing a right tail test, and that should be the case. Alright, if I'm going to do my steps again, both methods, step 3 for my p-value, since I'm doing a right tail this time, I'm going to do normal CDF of my test statistic to 1,000, since this is right tailed. Okay, let's get our p-value. So normal CDF 3.87 to 1,000. And be careful because this one ends up in scientific notation. So it's 0.4 zeros and then 544. Very, very small. Okay, step 4, I'm going to compare that to alpha. And this time, alpha is much larger. So my conclusion this time is going to be reject the null. So I know the null is not true. Okay? So that's step 3 and step 4 for p-value method. Now we're going to do 3 and 4 for critical value. Okay, so remember everything else stays the same. Now this is where it gets a little different. Okay, because I am doing a right tail test, when I do inverse norm, I don't put alpha in because alpha alone would give me a negative critical value. So I need to do 1 minus alpha. So I'm going to do inverse norm of 0.99. 1 minus 0.01. That's always what you want to do when you're doing a right tail test. You do 1 minus alpha. Okay? Now let's see what that is. Alright, I'm getting 2.33. Coincidence that, we're getting, well, it's actually not a coincidence because we're using the same alpha level. Alright, then I'm going to draw my rejection region. Okay, remember 0, 1, 2, 3. So 2.33, again, so right here. Okay. So this region starts with 2.33. And then I want to see if my test statistic falls in this region. Well, my test statistic was 3.87. Well, here's 3 way over here. So 3.87 is going to be way, I don't even know, way up here in the tail somewhere. Okay? So we definitely know it's going to be after 2.33. So because it falls after that, it's in your rejection region. So this time, you reject HO. Again, same conclusion no matter what method you pick. Alright, so my conclusion this time. This is one way to word it. I can say there is sufficient evidence to support the claim that the sample is from a population with the mean weight loss greater than 0. Okay, now why are we supporting when our answer was to reject? Well, remember, you're rejecting the null. Let's go back. What was the null? Well, the null was that the mean was equal to 0. So we're saying that is definitely not true, which means our evidence supports the alternative, which is the actual claim that the mean comes from a sample greater than 0. That's why we can say in our conclusion that there is sufficient evidence to support the claim. And remember, you would never say support the claim if the claim was actually in H sub 0. Big difference there, because you can never support the null hypothesis, but you can support an alternative hypothesis. Alright, so that is a right tail test. Alright, the last type is a two-tailed test. So we're going to look at this one, and then we'll be done with our Chapter A hypothesis testing. Alright, here is the third problem. Price of hotel rooms. This is in order to determine the average price of hotel rooms in Atlanta, a sample of 100 hotels was selected. It was determined that the average price, remember average means mean, in the sample was 108.50. Okay, if the population standard deviation is known to be $10, determine whether or not the average room price is significantly different from $112. Use a significance level of 0.05. Now this time it doesn't say to test the claims. Most time it will say that, but it doesn't always. So you have to figure out what your claim is. Well, your claim is actually this sentence right here. Determine whether or not the average room price is significantly different from 112. That's your claim. That's what you're trying to determine. Now the phrasing significantly different means not equal to 112. So this is called a two-tailed test, and the way you do this is a little bit different from a right or left tail test. Alright, so let's start our little process again. Alright, step 1, n is 100, list everything out. X bar is 108.50, standard deviation is 10, alpha this time is 0.05, and mu is 112, or the mean of the population there. Okay, so in step number 1, HO would be mu equals 112. H1 would be mu is not equal to 112. Okay, this is a two-tailed test. That's what it means by significantly different. Alright, test statistics still calculated the same way. Okay, mean of the sample minus the mean of the population over standard deviation over square root of sample size. Alright, so I'm going to do 108.50 minus 112, and this is just going to be 10 over 10, which is 1. So you're going to get negative 3.5. Now, when you're doing a two-tailed test, you can get two different answers here. You can get a negative test statistic or a positive test statistic, and that's going to help you in how you determine the critical value method. Just makes it a little bit easier. Since this is negative, we're going to think kind of along the lines of a left-tailed test. All right, number 3, we're going to do p-value first. So if you're doing the p-value, then you're going to do normal, CDF. Now you can go either direction. You can either do, well actually since this is negative, we're going to do the negative direction. Okay? The only thing is this is going to give you the left part. Since this is a two-tailed test, once you get this, you're going to multiply by 2. you're going to double your p-value. Okay, that's how you get or double the amount from either the left or the right tail. Since this is negative, I chose to do the left side. If this had been positive, I would do the right side and multiply by 2. So I do normal CDF, negative 1,000, negative 3.5, and I multiply that by 2. All right, and I get, again, another one in scientific notation. It's actually point, let's see, 3 zeros, and then 465. Okay, then I'm going to compare that to alpha. Alpha is definitely bigger, so my conclusion is going to be to reject, and we'll write the conclusion out in just a minute. All right, that's if you're doing the normal distribution. Just remember to double. Choose left-tailed if it's negative, choose right-tailed if it's positive, and just remember to double the p-value. Okay, if you're doing critical value, then you're going to still come up with your rejection region, but this time you have to do one thing that's different. With a two-tailed test, you want to do alpha over 2. So alpha is 0.05 divided by 2. Okay, so you're going to get 0.005. Okay, excuse me, 0.025, not 0.005. Sorry about that. Okay, you're going to get 0.025. Okay, so that's what we're going to do inverse norm of. So I'm going to do inverse norm of 0.025. Now, I'm doing the bottom end since my test statistic was negative anyway. Just makes it easier. If my test statistic was positive, I would do 1 minus this here. Alright, so inverse norm of 0.025 is negative 1.96. Okay, that's my critical value. I'm going to draw my region. Now here's another difference. With a two-tailed test, you need to put both ends. Well, you're going to have two critical values, the negative and the positive. So negative 1.96, I'm going to say about right here. Positive 1.96, about right here. So I have two rejection regions. Okay, that's because it's a two-tailed test. So this is 1.96. This is negative 1.96. Now since my test statistic was negative, I just want to see if it falls in this region. So you go back to your test statistic, which was negative 3.5, which will probably be over here somewhere. So it's definitely in one of the rejection regions. So again, we reject. Okay, that's the difference with the two-tailed test. Alright, so we're going to write our conclusion. And since we are rejecting HO, we're saying our evidence supports that the population comes from a sample where it is significantly different. So you're going to say there is sufficient evidence to support the claim that the population comes from a sample with a mean that is significantly different from $112. Now that doesn't tell us how much it is. We don't know how much it is. We just know it's not 112. So it's something different from 112. Alright, so that's the conclusion of Chapter 8 Hypothesis Test. We're going to do some more hypothesis tests with Chapter 11, and that will be in the next video.